Hello, everybody, and welcome to this extreme edition of Meet the Magicians. I'm very happy to be here. My name is Julie, or Juliane van Scherpenberg. I'm from the Max Planck Institute for Physics in Munich. And yes, today we will be talking about extreme blazars. So yeah, we have a bunch of very nice experts here who will explain us all about it. But first, some facts about us. So who are we and why are we doing this? So yes, I am a member of the MAGIC collaboration. We are an international collaboration. Here you can see all the countries where we are from, mostly Europe, but we also have members in Japan and India and Brazil. And yes, we are now up around 300 members. And we operate two beautiful telescopes on the Canary Island of La Palma, the MAGIC telescopes. Here they are. This is what they look like. And with these two telescopes, we observe gamma rays, which are the most energetic light particles that we can observe from the universe. And we study the extreme universe. So yes, extreme is a word that you will be hearing a lot today. We study the most extreme universe by observing gamma rays from a variety of sources. And today we will be talking about extreme blazars. So for this, we have three experts here with us on the stream. Let's start with Daniela. Hello, Daniela. Hi. Daniela is a postdoc at the University in Würzburg, and she has been a member of MAGIC for many years, for 18 years. So she has been there at the very beginning when the first telescope was built. So yes, you've been here all along.
Yeah, I remember when my first trip to the telescope, there was not all mirrors. We were drawing the cables for the motors. So yeah, I'm in the collaboration almost from the beginning.
Great. So you've really seen the entire, the entire history of MAGIC. That's so cool. For me, it's different. I only joined a couple of years ago. So actually LST was already almost there, the next generation telescope. Okay, so as a next expert on the stream, we have Axel. Hello, Axel.
Hello, everybody.
Axel is joining us from Zurich, where he is a PhD student at the ETH in Zurich. And well, still a PhD student, but not for long. So you told us that you handed in your thesis yesterday.
Yes,
how does it
exactly.
Feel? How does it feel?
It feels good. It was a very busy period the last few days, but it's nice now that it's a culmination of a few years, several years of work, and I managed to summarize everything in this document, and I'm really happy to reach the end and have this final document ready.
Yes, and we are very happy that you chose to celebrate this milestone with us here on the stream talking about blazars. So thank you for being here.
You're welcome.
Maybe that's also COVID restrictions that keep you from throwing a real party. But yes, so thanks for joining us. And yes, as a third expert, we have Vandat.
Yep.
Hello, Vandat.
Hello, everyone.
Vandat is joining us now from Bochum in Germany, where he has recently started a new position. And before you were in Finland.
Well, yeah, due to COVID situation, well, now I'm currently, it's at home office in Finland. So my home is in Finland, but I'm working in Germany, yes.
Yeah. So still in Finland, officially employed in Germany. And originally from Iran, so you've come a long way, and I'm guessing also big cultural changes have been part of your life.
Yeah, actually, I used to be an engineer and working in the construction sites, but then 10 years ago, I just decided to just come to the bright side. So I just come to study astronomy and astrophysics. So in Finland, then now from the beginning of this year, well, I am officially moved to Germany, but well, personally, I am still in Finland. Yeah.
Yes, and we are very happy to have you here on the bright side in astrophysics with us, and today here on the stream with us. Thank you.
Thanks.
Okay, so I think we can get started talking about blazars. Blazars are the real rock stars of our universe. I think they are highly unpredictable. Each of them is very unique in their own way somehow, and it's quite hard to find a set of rules where they all fit together. So let's get into that and into the details. And I think before we talk about extreme blazars and what they are, we should talk about what blazars are. So they are part of this group of objects. Let's not show that yet. I think we're not ready for this. So they are part of this subclass of objects called AGNs, but they're very confusing, and there are so many subclasses. And I personally get regularly confused by all the different types there are. So I think, I'm glad that we have the experts here with us today who can explain it to us. So I think, Axel, maybe you can walk us through a bit of the different types of active galactic nuclei, and what are blazars in particular?
First of all, I think to speak about this, I will start with a small flashback. It's good to do a small history review, go in the past. So the whole story about blazars started in the late 50s, let's say, when astrophysicists start to realize that in the sky there were some objects that looked like stars, but they were actually variable, and they were variable in a way that was quite different from typical stars, from most of the stars that we see in our galaxy. And the spectrum also looked quite different. So they're called, astrophysicists started to call these objects quasi-stellar objects, or simply quasar. So quasar is the mix between quasi on one side and stellar on the other side. And then along the years, it was realized that these quasars, quasi-stellar objects, they were far away from us. Using the so-called Doppler technique, we were able to measure their distance from us, and it appeared that they were outside of our galaxies. And the fact that we could measure their luminosity from such a large distance means that they were very powerful objects. And they were actually much more powerful, that they emit much brighter light than the sum of the light emitted of stars in a typical galaxy. Then we also realized that they were extremely, as I mentioned to you, they were quite variable on very short timescales. And in order to explain this very short variability, they must be very compact. So we have these very compact objects far from us that are extremely powerful. And we started to observe more and more of these quasars, and we realized that they look also very different between each of them. Some had some really bright emission in the radio, while some others are some very faint emission in the radio. Their spectrum looked quite different. There are also some different morphologies and so on. So we have this very large variety of quasars. And along the years, we kept observing them, and we gathered a lot of data from many telescopes. And now astrophysicists start to think that these objects can be kind of unified in a single type of object, and they are very similar, and they are built from building blocks that are common to all of these quasars. So maybe we can now show an image, artistic view of these so-called quasars. So on this image, this is an artistic view. Of course, we cannot go there and do this kind of a picture, so it's an artistic representation what are quasars. So at the center, what we see is a black hole, a supermassive black hole, which is extremely heavy. It has masses that are between millions and billions of masses, of solar masses. This black hole is accreting matter, and it's creating this kind of accretion disk around the black hole. You can see it's here, this kind of accretion disk that is formed around the black hole. And then also around this accretion disk, we can have a so-called dust torus. It's like it's a torus made of dust that is also orbiting the black hole. And from the center of this object, we have a relativistic plasma jet that is emitted. You can see this huge structure coming out from the black hole. And this relativistic plasma jet, we detected some structures in it that are moving at speeds very close to the speed of light. So it's going at relativistic speeds. And these jets are really huge structures in the universe. They can be from kiloparsec to megaparsec. So just to give you an idea, the size of the galaxy is around 10 kiloparsec. The size of our Milky Way, the radius of our Milky Way is about 20 kiloparsec. And these jets can be easily between kiloparsec and megaparsec. So it's really huge structures. And in order to explain the differences that I mentioned to you between the different AGN, these different active galactic nuclei that we observed, we say that the orientation relative to the jets can explain the different spectra that we measured within the active galactic nuclei. And why we are very interested in observing this blazar is because there are candidate sources. So first of all, I should say that blazars are this active galactic nuclei that we are seeing with a very small angle relative to the jet. So basically the jet is pointing towards us. And because this jet is pointing towards us, due to some relativistic effect, the emission is strongly enhanced. It's really bright. And the emission is also slightly shifted to higher energies. And in this jet, we think that there can be some very strong acceleration of particles and possibly cosmic rays at 10 to the 20 electron volts. So this is 10 orders of magnitude higher than the energy that the CERN can reach. And we still don't know where this particle come from. And we think that the blazar can be sources of these cosmic rays.
Okay, so that was a lot of information. So, okay, I will try to wrap it up. So we have distant objects that historically looked somehow like stars, but we figured out that they are not really stars and they are different in many ways. And then we figured out that they are far away, so they are distant galaxies. And all these different types that we saw and all these different types of spectra can now be explained basically by us looking at the same type of object but from different angles, right? So this is kind of this entire picture that we now have. And we saw this nice picture of the black hole in the middle, the torus, and then the jet coming out. And okay, in terms of blazars, when we talk about blazars, it means we are looking in this jet. So the jet is pointed directly towards us at Earth. Okay, cool. So now we have established what are blazars. But now we want to talk about extreme blazars. So maybe Vandad, can you explain to us what makes extreme blazars so extreme? Why are they special?
Well, before that, I would just like to ask, okay, how we are studying the blazar. So normally, if Marina, could you please show the spectral energy distribution? So the first picture of that. that we study the blazars by studying the spectral energy distribution. So they, as you can see in this figure, so we have the amount of emission that we are seeing on the Earth on the y-axis, and then the energy of the emission in the x-axis. So this is a typical look how the blazar, how we are seeing the blazar, the emission from the blazars on Earth. So as you can see, these two bump. So the first one is due to the synchrotron emission, which is electrons spiraling inside the magnetic field, so which makes this synchrotron emission. And the second bump is the inverse Compton emission. So for the inverse Compton emission, well, we can just, you can see just how they are produced in the next kind of a small GIF or movie. So a photon and an electron collide to each other, and then the gamma ray, which is will go back as inverse Compton emission. But this is a typical view of a blazar. But what is an extreme blazar? So there are different characteristics of the blazars, and we astrophysicists try to just categorize these blazars into different categories. So typical blazars normally have their synchrotron peak, well, below 1 kilo electron volt, so in the X-ray band. But extreme blazars have their synchrotron peak above 1 kilo electron volt. That's why we call it these blazars, which have extreme synchrotron peak, or and also extreme inverse Compton peak, extreme blazars. So they are not regular blazars, which have their synchrotron and inverse Compton peak somewhere in the lower frequencies. And this is what we call extreme blazars, and they are kind of they can be also, we have two types of extreme blazars. So there are some objects that become extreme from time to time, but there are other objects which are by nature which we believe that they are always extreme. So it means that those peak in the spectral energy distribution is always above those limits that we put it as astronomers. This could be part of observational biases, but it could be also fundamentally they are different. But how we can understand that? It's just we have to observe more and more to just get to know more sources, and we will discuss the different two types in next minutes.
Exactly, right. So we will talk about extreme blazars and these two types. We've heard that some of them are always extreme, but some are not always extreme. And we've also mentioned in the beginning that these blazars themselves, they are really highly variable sources. So how do we do this, and how do we observe them at the right time when they are maybe in this extreme state, and how can we monitor this? For this, I think Daniela is the right person to ask, because first of all, she is also a member of the FACT collaboration, and the FACT telescope is a telescope that monitors blazars specifically for this purpose. So can you tell us a bit about what FACT does, and how the monitoring program works?
Yeah, maybe as we just talked about that the sources are variable, let's have a look how this looks like. Like if we say, okay, how does the flux evolve versus time? I think we have a light curve that we can show. Yeah, so this is an example that FACT has measured, one of the blazars. Each of the blue dots that you see here is the observation during one night. This can be 40 minutes, this can be 6 hours, depending on the visibility of the object. But you can see that there is very strong flux variations from one night to the other. So on these time scales, extreme things must happen. And you also can see that sometimes the flux is very high one night and the next night it's very low, or the other way around. So that's why we need the monitoring. That's one aspect. But before I come to this part of what FACT covers with the monitoring, I'm not only a scheduler or doing the observation plan for FACT, but also for MAGIC. And there's one other very important aspect. So we've seen that the sources change their flux from one night to the next, which means we need dense observation cadence. But then the other thing is we've seen that they emit light on a very large scale in energy. And I think we have also a picture of a spectral energy distribution with the measurements from different instruments. Maybe we can show this. Yes, exactly. So you see here many different colors, and each different color is a different instrument. So you see that in radio and optical, there's a lot of different instruments. In X-rays and gamma rays, not that many, but still, you see a lot of different markers, a lot of different colors, and that means a lot of different instruments. Now, combining these two information, we have strong variability and a wide energy range to cover. That means a really big challenge for the scheduling, because we have to, on the one hand, match the cadence of the observations, so observe the sources regularly. And on the other hand, we have to coordinate with different instruments. And that's the really challenging part, because you always have to plan ahead. And there, of course, it also depends with which instrument we are talking about. For FACT, we are talking about a small sample of sources, but for MAGIC, we have a lot of different physics cases. I mean, if you've been following the series of events, then you know already about gamma ray bursts and the different types of sources. So we have a lot of different physics cases to cover. And as a scheduler, I can tell you that it's sometimes really difficult to match all this into the observation plan. So how do we do that usually? At the beginning of each month, or strictly speaking, we are not talking about month, but for the time from full moon to full moon. So that's the time when there's a new shift crew on the island comes around full moon. And then we have until the next full moon, our observation period. So at the beginning, around full moon, as a scheduler, I receive the different requests about multi-wavelength observations. So for example, Axiom contacts me and tells me I would like to observe this source once a week and coordinate it with X-ray satellite observations. And then I need to fit this into the schedule. And maybe to give you an impression how that looks like, we can show an example of a schedule. So you will see that, here you see now the different numbers are different objects. And also you see different colors, different markers like lines in the boxes. Lines in the boxes always means that's something important. That's like either a multi-wavelength observation. So for example, coordinated observations with SWIFT or with some radio telescopes. Or it can be what is called target of opportunity observations. That's again a bit different thing. For example, if some radio astronomers or X-ray astronomers realize that one of the blazars gets really bright, then they inform us and they tell us, well, you should also look there. And this is when we get such a target of opportunity request. And then we have to really put all the different observations into the schedule and match all that. And you can see then it can be quite crowded and it can get challenging, but I think we get great physics out of that because we can flexibly handle that and react to really interesting events ongoing, for example, in blazars. And we're also going to talk about such an interesting event, which was not triggered from X-ray or radio observations, but that was triggered from fact. And so maybe before I come to that observation and that story, let me show you fact. So this is the fact telescope. It has 3 meter diameter, so compared to the MAGIC telescopes, it's smaller, but it has a very special feature. It has a camera with novel photosensors. These are, so the name of fact, first GAPD Cherenkov telescope. The GAPD in that name, that's these photosensors. It's Geiger mode avalanche photodiodes. Another name, maybe you have heard of that, is silicon PM. So it's silicon-based photosensors. They are also used, for example, in medical physics. So there's interest from different disciplines also in that. And we operate our telescope with this type of camera, and that gives us a lot of advantages and a lot of possibilities. But maybe before coming to that, let me show you where fact is located. I think we have a view of the site seen from the top of the island, where you can see the different instruments. Marina, can you maybe bring that up? I meant the other one, but that's also fine. Yes, that one. So you can see here the 2 MAGIC telescopes and also the large size telescope from CTA. And in between MAGIC 2 and CTA LST, that's fact. So just to give you an impression on the sizes. Now, as mentioned already, fact is mainly doing monitoring. And for this, the photosensors are very important. And yeah, the thing I mentioned before, that we have this target of opportunity. Okay. Sorry.
Okay. Okay. Let's.
I thought we moved directly to
maybe. Okay, summarize what you told us because it was. Sorry.
Oh, fine.
Yeah. So okay. So we covered the aspect of doing multi-wavelength observations and how difficult and challenging it can be to schedule all of these different observations, but they are really important, and we will come to the physics of why they're important later. So that's the scheduling part, and then we have the different instruments who do monitoring regularly of the different sources. One of which is fact, that alert us in MAGIC to actually then schedule it at a certain source and tell us, okay, this is interesting, have a look at that. And then we do it, and when we go through the whole thing of changing the schedule last minute to have it actually observed in the night. So fact is a great telescope for that, because it covers also this more or less the same energy range that we cover with higher energies, and it is especially made for monitoring and a great tool for that, because it's sensitive during even high moon levels, and it can work remotely and automatically. So did I cover everything important about fact, or did you want to mention some more? Daniela?
Well, if people are interested, I can tell a bit about the robotic operation or the moonlight observations, but we could also move on to the trigger that we sent to MAGIC on this extreme blazar. I mean,
yes, I think let's move on, because I think people are mostly maybe interested about the physics cases. So yes, tell us the story about this interesting trigger that happened from fact.
Yeah, so as I mentioned, I'm also doing the scheduling for FACT. And at the beginning, when we decided which sources to observe, there was a gap in the schedule and we were not sure which source to put there. And then somebody mentioned, oh, there is this source, 1ES 2344 plus something. And we said, okay, why not? And we observed it for several years and nothing special happened. And I really thought, oh, that source is boring and maybe we should replace it. But then 2016, suddenly the flux increased. And of course, we sent a trigger to MAGIC. And then the source was observed. And well, I think about this part, then Axel can tell you more because he then took over this project in MAGIC and did all the analysis and interpretation.
Yeah, so it ended up being a super interesting event, right? And we published a paper about it last year. Axel, you were one of the corresponding authors, and you did a lot of analysis on this data set. So can you tell us a bit, maybe first a little bit about the source, what
Yes.
some properties?
This was actually part of my PhD work, PhD research. So this source that we call 1ES 2344 plus 514. This is the name of the source. There are many sources in the sky, so we use number to differentiate them. This source is a very particular blazar. Yes, you have the name here on the left. It shows some extreme behavior that Vanda had explained to you before on a temporary basis. So sometimes it is extreme and sometimes it is not. And we would like to understand more why it is so and what is triggering this extreme behavior. What makes this source an extreme blazar sometimes and a normal, let's say, more standard blazar. And another great thing about this source is that it's rather close from Earth. It's among the closest blazar, and it's also rather bright. So we can really study it with great detail, and it's a unique opportunity to better understand sources that are sometimes extreme and sometimes not extreme. And
okay. Yeah, so this is basically why it made the cut to get into the fact monitoring, I guess, because it's close and sometimes something interesting happens. But so what was so special about this specific event? What happened then? What we observed then?
So FACT told us that the source was in a high activity, and then MAGIC started to observe. So when I say high activity, it means that the flux, the number of photons that the source was emitted per unit of time was much higher than its typical behavior. And MAGIC started to observe the source. And maybe now we can show a spectral energy distribution, a spectrum of this source. This is how it looked like in August 2016. So what you have to look here are the red data points. These are the measurements that was performed in August 2016. MAGIC is observing at the rightmost end of the spectrum at the highest energies. And then we collected a wealth of data at lower energies to have a behavior, to characterize the behavior also at lower energies. And you can see that the lower energy component that is due to synchrotron radiation, as Vanda explained to you, was peaking at energy above 1,000 electron volts, so above 1 kilo electron volts. And so it behaved as an extreme blazar in this month of August 2016. And so we tried to explain what is the behavior of this source, and it is not an easy task. We think that within the model that the Vanda explained to you, this synchrotron self-Compton model, this was the black line that was showing, that was visible in the plots. Maybe we can show again maybe the previous, yes, this one. So this black line here, this is the synchrotron self-content model that Vandal explained to you. And you can see that we can nicely describe the ray data points. So we were able to explain the behavior of the source. The complicated thing is that to achieve this good description of the data, we needed some very extreme parameters. So to be very brief, what I mean here, some extreme parameters, we had to invoke an emitting zone in the blazar, which had much more energy in the particle than in the magnetic field. So there was very strong imbalance in the energy, the way the energy was distributed between the magnetic field and the particles. And this is complicated. Usually in physics, we always try to reach equipartition. So I have a question here. The blazar is 1ES 2344. So as I was saying, we always try to reach an equipartition between the magnetic field density and the particle. And here it was highly unbalanced. And this is not easy to explain within standard acceleration scenarios. So we still have some mystery there, and we would like to keep observing this source to better understand first when it is extreme or not, and how can we explain such measurement within a synchrotron self-content model.
Yeah, so this is kind of what I mentioned with these extreme blazars. They are really they don't fit into the rules, right? You want to have in a the magnetic field and the energy, electron energy in a certain level, and now with the specific source and the specific flare, it just doesn't work. Did you also, is this like the only model that kind of would make sense, or would there also be options in a different model framework that could also work to explain this kind of flare?
Yes. So in this particular paper, we explored another scenario where the gamma ray emission, so the GeV and teraelectron emission was emitted by also synchrotron radiation, but protons, not electrons, protons. And we call this kind of model hadronic scenario because they are emitted by hadronic particles, the protons. We could also nicely explain the measurements, the red data points that you saw before in the spectrum. We could also nicely describe them, but we were also heavily out of equipartition. So there was still a strong imbalance between the energy density stored in the magnetic field and in the particles.
Okay.
So we explored this different scenario, but still we did not reach a totally satisfactory picture.
Okay, so difficult and staying interesting, and it's definitely worth to observe it in the future, and hopefully we can learn some more. And you kind of mentioned now, and we've talked about it, how important it is to not only observe these blazars at the energy range that MAGIC can cover, so not only in gamma rays, but also at the other wavelengths in the electromagnetic spectrum. And Daniela told us about all these difficulties on managing and coordinating all these different observations from all these different instruments. And because this is such a difficult task, we actually have multi-wavelength coordinators in our collaboration, and Vandad is one of them. So, Vandad, what is it like to be the multi-wavelength coordinator in MAGIC, or one of the multi-wavelength coordinators in MAGIC? And what is your job? What do you do? Oh, I can't hear you.
Okay. As you already hear it. So Daniela, Axel, and also Julie just said that, okay, multivalent data are important to just understand what is happening in these extreme sources, or even the blazars, non-extreme sources. So for this, in the Magic collaboration, we have a group which is responsible for arranging how these multivalent data, a stream of multivalent data, into the scientific papers. So, as a multivalent coordinator of the Magic, well, I am tasked to make sure that all of the principal investigators of the sources and proposals and observations know the importance of the multivalent coverage, and provide them with the guidelines and tools, and also that they need for their scientific needs. Moreover, well, every once in a while we introduce a new instrument which will be launched in near future, or they are working, and we as a magician are not very familiar with them. So we are trying to just make the magicians more familiar with the multivalent instrument. Yep, that is kind of the tasks that I already have as a multivalent coordinator of Magic.
Okay. So what is it like to work with all these different collaborations, all these instruments? I'm guessing that that entails having a lot of contact also with people outside of the Magic collaboration to get all the facts and, learn about all these instruments. So what is that like?
Well, working with other instruments is always good. You will learn more, and well, how the other people are seeing the sources that we are seeing in the Magic. So there are different views of the sources of different sources. And well, I am part of Torla blazar monitoring program, which observed many blazars in the optical band. And also I used to work with the Metsawi radio observatory, which this observatory is also monitoring many of the blazars and AGNs at 37 gigahertz in the radio band. And yes, that's kind of it is the coolest part of my job, to just be involved in many instruments and knowing about the what instruments are working, how the others are looking at the same objects.
Yes, cool. Yeah, I can imagine that must be very interesting to get so many different views of the same object, and then it's like a puzzle, putting all the pieces together, and in the end, hopefully you manage to get an image that makes sense. But we heard before also how difficult that can be. So is there anything you don't like about being a coordinator, or is it all unicorns and rainbows?
So, well, actually, there is one thing, because well, from time to time, I have to just go after my colleagues. So, okay, please report us if you need something, or if we can bring you something that you are forgetting it. So, just put us in, or kind of top of your to-do list. Well, if we know that what they are doing, so we can just coordinate it and arrange it a better aspects on it. So, just putting everything in order. It would be easier to order it, but if everyone randomly goes everywhere, then it's really hard to find it. This is the part that I don't like it. And today, today we just submitted one proposal to one of the X-ray telescopes, which we are going to observe some extreme sources with the AstroSat, the Indian X-ray telescopes, together with Magic.
Oh, nice. Yeah, so this was kind of partly maybe addressed to Axel and Daniela, being the ones who are observing these sources and should give you feedback. So Daniela, maybe what was your experience? You are also analyzing and working with these sources. So what's your experience of analyzing all this data, or working with these different instruments?
Well, working with different instruments is for sure very interesting, as Vandal said, because the different instruments have very different characteristics, and you learn a lot. And also the communities, you have to learn different languages. Like the radio community, they talk about frequency while we talk about wavelength, just a very simple example. And there's more difficult examples, let's say. But Vandad, I also know this running after people as scheduler. I also have to do that.
Okay, so Axel, what's your experience? You're young and fresh PhD. So what has it been like to work with these instruments in your PhD?
It has been awesome. I really enjoyed it. This was a great experience. So I must say, I think it's rather rare in physics that you can work with so many different instruments as we do within the MAGIC collaboration. It's not often that scientists can deal with data from tens of instruments, and this is what we're doing here, and it's a really great experience. And this makes the research extremely dynamic. So we may have, for instance, the Fermi satellite that is orbiting around the Earth, telling us that this blazar is making some strange behavior, and then we will suddenly point the telescope, the MAGIC telescope there. And this is happening on an unpredictable way. So this renders the research extremely dynamic, and we have to deal with all these instruments. It's really nice.
Okay, cool. So before we go to the questions, let's talk a bit about a paper that we also brought out last year, which actually has all the also about extreme blazars, but the ones that are not variable but always show this extreme behavior. So Vandad, you were one of the corresponding authors on this paper, and you did a lot of work on it. So could you quickly talk us through what this paper is about and what we can learn from it?
Well, this paper was the first time that we systematically searched for the new extreme blazars in the very high energy gamma ray band. And we tested many different, three different theoretical emission models to find out which one can describe the data better. So that was the aim of the paper.
Okay, so this was the first catalog of its type, and how many sources do you discuss there?
Well, we just report the observation of the 12 different sources, and well, some of them were known very high energy gamma ray sources, but some of them were new, and we just managed to just increase the number of the new sources by a factor of 2. So before this paper, we have only 4 or 5. Now we have 8, 9.
Okay, so that's
type of object.
It's quite a nice increase, but maybe for, I don't know, astronomers watching and doing population studies on I don't know how many million stars, it doesn't sound as impressive. So do you think it will grow in the future? Will we get to add more sources like this to the catalog?
Let me reveal some news. Yes, sure. There is a new catalog coming on its way. So, and we have also new sources, and also we are studying kind of the old sources that we already known as a known very high energy gamma ray emitters.
Okay, so stay tuned for the future.
Yes.
Okay, so thank you for this overview. I think we've covered a lot of information, and I think we have quite some questions from the chat. So let's now take some time to answer them. So we have one by David. He asked if he heard correctly that we're talking about cosmic rays with energies of 10 to the 20 electron volts.
Yes, this was correct. These are really the highest energies cosmic ray that was detected by different experiments, the Auger detector, for instance. And these are the most energetic particles we detected so far. And we still don't know the origin of this particle. And active galactic nuclei might be sources of these cosmic rays.
Yeah, the tricky part about those is also that they are not very numerous. So you need huge detectors to collect them and a lot of time. And then having few of them from maybe a direction of an active galactic nucleus doesn't help much yet. So there's interesting stuff to come in the future, I think.
But that's also why gamma rays are so important, because we don't know the direction of these cosmic rays, but then by observing gamma rays and finding out the processes, that's how we can maybe learn, right? Yeah.
Yeah, exactly. So I just want to add that. So we already have one coincidence of observing cosmic ray in the PEV regime, and we on the same time we have the gamma rays, a source with the gamma ray flares showing a gamma ray flare. So it's just the neutrino blazar is the famous example of this. So, but we are searching for the second and third one.
Yes, so for us it's still like counting the single sources, but we will get there. Okay, so we have a next question by Pavel. Which type of lasers do you like more, BLX or FSRQs? So maybe for the people who don't know, so FSRQs is short for flat spectrum radio quasar, and BLX are the types of sources we were talking about. Can you maybe quickly tell us what is the difference between the two, and then you can tell us which you like more? I don't know who wants to take this question.
Well, I will take it because I have a strong opinion on this. Well, first of all, let me just tell you, okay, what is the difference? So the difference is simple. So if you look at the optical spectrum of these two type of sources, one of them is showing the emission and absorption line, and you can clearly detect emission and absorption line. So this is because we believe that there are some difference in the physics, in the intrinsic properties of these two sources. Okay, so FSRQs or flat spectrum radio quasars are showing those emission and absorption lines, while BL-like objects don't show those emission lines, or they are kind of obscured by the emission from the relativistic jets. My favorite one is the BL-like object. So this is the kind of the thing, because FSRQs are, but they are more variable and just going up and down more rapidly. So I just like the BL-like object.
A bit more steady. Among all these variable sources, the BLX are the more stable ones. What about you, Axel? Which one do you like better?
So, yes, we should say that the Airstream blazars we spoke about until now, they belong to the BLAC category, just for clarification. But I'm also like Van that I prefer BLAC objects, but for different reasons. So Van Dad mentioned that there are some emission lines that we detect in the optical spectrum from quasar. And this means that there are some really bright and some different intrinsic properties with respect to BLAC. This means that this emission line can also contribute to the emission in a very complicated way. And this renders the interpretation of the emission of FSRQ also quite, let's say, much more complicated than BLAC. You have to invoke different radiation fields and so on if you want to interpret their spectrum. It's also very interesting, but in sense, the BLAC are easier to understand.
Okay, BLACs are easier, more stable. Daniela, do you have, what's your opinion?
Well, I can also add my reason why I prefer BLAC.
Is it a new one, or is it the same?
It's a new one. I mean, I'm looking at it from the fact perspective. FSRQs are not, they are too faint for fact. So of course I prefer BLAC.
Okay, look, this was a great question, even though it was a funny one, because we actually learned a lot from all your opinions and all your explanations. So thank you for this question. So let's move to the next one by Jim. Are the speed of the particles affected by traveling through interstellar dust?
Well, I would say the speed not, but the amount. So we might just lose part of them, depending on the energy and depending on what the dust contains or what is in the way.
Right. So those that make it through, but we might lose some on the way. Yeah. Okay. We have another question. One by Felix. Is it possible to attribute variability to some extent to some sort of shadowing effect and not just a variation on the emission side? So is it all intrinsic in the source, or is it something that's just somehow blocking?
Well, it depends how we just interpreted the variability on that. So, actually, it is still on the debate. So, because we cannot say that, okay, so if this variability is coming from a standing shock in the plasma of the jet, or it is because of the reconnection of the magnetic field inside the jet. So, to some extent, yes, and to some extent, no. Well, it could be intrinsic, or it could be from the different theoretical scenario that we are putting there.
Okay, thank you. Do we have more questions?
If not, then we can maybe add some other shadowing effect. I mean, intrinsic to the source, but as we always have something like the Earth atmosphere in between, right? There can be also kind of shadowing from this, and this is something we have to deal with then in the analysis. So from the analysis point of view, to differentiate between real astrophysical variability and maybe some apparent variability due to clouds or some other effects. This is also a very important thing that we have to deal with. And yeah, so look exactly how the weather was is an important
yes.
thing to do when analyzing data.
How fun is it to analyze data taken under not so perfect weather conditions? Axel, what do you think? How complicated does it get?
So it gets, of course, more complicated when you have a dusty atmosphere or some clouds in the sky. You have to correct for it. You have to take this into account when you want to extract the fluxes, so the number of photons emitted per area and time. And but luckily, MAGIC is equipped with a so-called LiDAR. I probably won't go into detail here, but this instrument is there in the sky, and from the light that is backscattered on ground, we can detect the clouds in the atmosphere. We can locate them. We can estimate by how much the absorption is, by how much the light is absorbed, and so on. And with this information, we can correct for the effects of a non-optimal atmosphere.
Yeah.
So from this point of view, we are lucky.
I think we had that also in the 2016 flare in August. So there we had something even worse than Kalima, because it's more difficult to spot on images of the sky, and it's Kalima. I don't know if the audience knows what Kalima is. Maybe we can show a picture of that.
Yes, I think we have one. Yeah, so this is the radar image, one radar image of what we mean when we talk about Kalima.
Yeah, so basically Kalima, a different name for that is the sand dust that is transported in the so-called Saharan air layer. And the Canary Islands, where MAGIC is located, is just next to North Africa. So you have the Sahara very close by. And then you can have the situation that in an air layer between, I think, 1.5 and 5.5 kilometers above sea level, there is the sand dust. And the telescopes are at 2.2 kilometers above sea level. So you're just in the middle of this air layer, and you can also clearly feel it. I've once been there during Kalima, and I was outside at night in t-shirt at 2,200 meters. And at some point I realized, oh, I forgot my jacket, and I didn't really feel it because it had 20 degrees at night. That was really, really weird.
Yeah, it can get like really hot and stuffy and super dry. I mean, maybe some of the people in the audience remember that earlier this year, some of the Sahara dust came to Europe. And if you went outside then, you could also feel it, and like the air was dry and you couldn't see very far. And, you know, it was deposited on all the cars and all the windows. So imagine that, having that every year on La Palma, where our telescopes are. It can be quite, well, difficult for the analysis and for the data, and, well, also annoying for the shifters who are there. Okay, so I don't think we have any more questions from the audience. So to wrap it up, I would like to ask you what you look forward to most in the maybe upcoming 5 to 10 years concerning blazars and extreme blazars. What do you think will we be able to learn? What new detections or discoveries can we make? Let's start with Axel, maybe.
So in the upcoming years, there will be this so-called Cherenkov telescope array, which is the kind of the successor of instruments like MAGIC, and it will be also much more sensitive, and we will be able to detect a much larger amount of blazars, and also blazars that are also much further from Earth. So we will be able to collect and measure much larger amounts of blazars and start to perform some population study. Right now, in the very high energy range, so in the energy that where MAGIC is measuring, we only have around 150 sources, and this is quite limiting us from performing population studies. But with CTA, we will drastically increase the number of sources that can be detected, and we will be able to do this, start performing population studies. So this is quite exciting.
Okay. So Daniela, what about you?
Well, for the extreme blazars point of view, I'm looking forward to some multi-wavelength studies that we have started. So asking data from X-ray satellites to coordinate with the MAGIC observations. And I think there we will learn interesting things, like see, are the sources always extreme or just sometimes, and really correlate that with each other. And I mean, we're trying to get these observations with X-ray satellites in several years, and it's sometimes tough to coordinate it. You always have to apply for the observations, and then with COVID, some of them got canceled. So I hope that this time it goes through and we will get a great data sample. And of course, that the weather will play along with
it. Yes, that's always the important part. Okay, cool. So Vandad, what do you look most forward to?
Well, actually, I am hoping that with the new generation of the imaging air Cherenkov telescope, like Cherenkov telescope array, so the burden of the MAGIC schedule goes down, and then we can observe known sources more, and we will have a really nice light curve of every known sources within the reach of the MAGIC telescopes. And after 5 years, I think that MAGIC is operating right now, I think about 18 years. So, and with 5 more years, we will have a really long, nice light curve of many sources for 23 years to 25 years, that we can start analyzing them and just see that, okay, what is happening in the very high energy gamma ray band. So similar to the work that people did with the optical band or radio band, because they have a really long light curves of every source. So this is kind of the things that I hope that we can achieve that so in the next 5 years.
Okay, so Cherenkov telescope array has the two advantages of increasing the number of sources, but also taking workload off MAGIC to give MAGIC more monitoring or like longer exposures on the different sources. Okay, that's a nice aspect to it, I guess. Okay, so I think we're coming to an end. Thank you so much, everybody, for joining us today. And I think we also now have to say a big thank you to Marina, who was helping backstage. There she is. Hello, Marina. Thank you so much.
You were fantastic.
Yes. So yes, thank you again. We had a great time. I think the audience did too. And well, let's see what the future holds for extreme blazars. Bye.
Bye.
Goodbye.